Hey guys, welcome to the AI 311 tutorial, and we're gonna do briefly wave propagation in different media. Now this is a series of 3 to 4 videos, each not exceeding 6 minutes, and I pray that this understanding and all that we needed to understand this will be giving unto you. Alright, so quickly we'll start with a general view of wave propagation in all media, in different media, the general formula before which we can just tweak to fit the different types. So we have we start with our Maxwell's equation. We start with div E is equal to 0, div B is equal to 0, curl E is equal to the B to T, or minus the B to T, and then curl B is equal to J plus epsilon the E to T. Now how do we come about that? You'd recall that if this is a conductor in diagram 1 here, this is a conductor, then current flowing in this direction, you can see the arrow, and this is the surface area, CSA. This is your CSA. Alright, so you'd see that current flowing in this direction is causing a moving electric field, and a change in electric field causes a magnetic field, and that's according to Maxwell. That is the whole point of the Maxwell, that a change in magnetic field would give you an electric field, and a change in electric field will give you a magnetic field. So both of them are always intertwined in this kind of lifelong cycle. Alright, so that is the basic concept of your Maxwell. So you'd see that the magnetic field created is in a loop, while the current moving is straight from left to right. Okay, now we know that. So look at the diagram just here, just a little bit overview in case it's not too easy to understand from the other diagram, but that is the smaller one over here. Alright, now why is div E 0? I mean, I thought all electric fields come out from a source point, from a charge. Well, it's different in the case of a wave, because in a wave you can see that the fields come up and they're increasing, and then they're decreasing, and then they're increasing. But as you can see, they are not coming out from any one point. They are parallel. And div says that the field is actually coming out from one point. So there's a source in which everything diverges round, spreads round. That's the word diverge. So in a wave, you'd see that there's no divergence of electric field nor magnetic field. So your div E would equal 0. Your div B naturally would equal 0 because magnetic lines don't have magnetic monopoles. So here, no magnetic charge have been discovered yet. So we're still in the dark ages, I guess. Then your curl E. Now curl E will have a value because your current can move in a circle. Current can move in different directions. Your field can move in circles. So your curl E, saying that the moving curl E, changing electric field, would give you the B to T. So a change in electric field would give you a magnetic field, and your curl B, which is naturally the case because B always curls, is going to give us it's J plus epsilon the E to T. Why J? J is the current passing per area, so this current per this CSA here will give us our J, and we say it produces a magnetic field. So current produces a magnetic field. Also a change in electric field produces a magnetic field. Okay, so we got that down. Now let's quickly delve into the mathematics behind this. Alright, so taking from let's start with I'm trying to use, okay, let's pick the last two equations. So I start with curl E equal to minus the B to T, but B is equal to mu H. So I can say that I can replace all the B's with mu H. So this the last one, curl B, is equal to J plus epsilon d E to T. So I can just replace that with H. So that means I can say that curl H is equal to is equal to mu. Alright, there's no u here. So that'll be J plus epsilon to E to T. Alright, so this is your last Maxwell equation. Okay. Now I replace E there. So this is going to be E equal to minus mu. Now mu is more or less a constant, mu the H the T. Now it will be very suitable to convert this to your frequency domain, because this isn't time domain. So once converted to frequency domain, you can use Laplace, using Fourier, whatever you have. But using Laplace, the Laplace of a derivative will give you, so from we're converting from time to frequency. So you have the H, the T is going to be JWH, and the E, the T is going to give us JWE. Now the initial conditions are removed. Well, we expect that the sources are 0. Okay, so if I put this back in the equation, I would get change in H. It's going to give me J, capital J, plus small complex J, W, epsilon, E. And your other one is change in E, curl E, equal to minus JW. Remember there's a mu. JW, mu, which is like U, H. Alright, so this is our new Maxwell equation. This is what we're going to be working with throughout the time of the tutorial.